So if you have a two-dimensional wing, you just have an airfoil and you have a single aerodynamic force vector, which is this red airfoil here. But if you are looking at a three-dimensional wing from a side view, then you will not really have a single force vector, but instead you will have a different force vector for each span-wise section. And if you combine those individual force vectors, you will see something like this. So these blue arrows are the side view of the blue force vectors in this diagram here. So in the middle section you have the local force vector very close to that of a two-dimensional wing, but as you come closer to the wingtip you have less lift force and more drag force, which means that you have the total force vector tilted backwards, as you see here. Now let's also take a look at a front picture, a front view of these forces. Let me talk about this one first. So this is a two-dimensional wing which has an infinite wingspan, and you see these force vectors perpendicular to the wing flow, to wing surface, and they're all parallel to each other. So you have the same lift distribution. So this red line shows the magnitude of the lift force created at each span-wise location. But for three-dimensional wing, the lift distribution looks like this. So in the middle section you have the largest lift force created, but due to the three-dimensional effect at the wingtip, the lift force gets smaller and smaller, and finally at the wingtip you have no lift force created at all. So this is the difference between a two-dimensional versus a three-dimensional wing from a front view. Okay, so in two-dimensional flow, the only thing that determines the aerodynamic performance is the airfoil, but in three-dimensional wing, the wing planform shape is important as well. In other words, if you have two wings with the same airfoil and same total surface area, if they have different planforms, then the total forces created will be different. Okay, so let's take a look at these two wings as an example. So suppose that the surface area of this shape is the same as the surface area of this wing, and they have the same airfoil. Okay, so this has the same airfoil. The shape of the airfoil is the same, but the chord length is different, obviously. So you have a small chord length here, and you have a changing chord length. But let's assume that the wing surface area is the same. Okay, so if you compare these two wings, which one of these two wings do you expect to create more lift force? Which one? This one? Okay, good. So does everybody agree with this? Do you all think that this wing should be creating more lift force? It's good that you all agree on this, and that's obviously the case. And the simple fact for that is, we said that these three-dimensional effects are nothing but creation of these vortices at the wingtip. And if you just compare these two wings, you see that this has a larger wingtip area, right? The wingtip region is greater than this wing here. So you have a smaller wingtip region. So in other words, you have the vortices created here in the entire wingtip here, whereas you have a much smaller wingtip region. That means the three-dimensional effects will be smaller on this wing. So even though they share the same airfoil and the same surface area, if you compare the lift forces created by these two wings, you will see that this is better. That's because the losses due to the wingtip effects will be smaller on this airfoil. Okay? So again, in a two-dimensional wing, you just have an airfoil that determines the aerodynamic performance. But if you come to a three-dimensional wing, then the wing planform shape becomes important as well. Okay. So let me come back to this first slide. I really forget about talking about this ratio here. Lift force is very important for us because that's what makes an aircraft fly. But the lift force by itself is not very important. What's more important than that is the ratio of these two forces. Because while you want the lift force to be as large as possible, you also want the drag force to be as small as possible, because a large drag force means you need a large thrust force to balance that, and large thrust force means you need a bigger engine, right? A bigger engine means you have a heavier engine and a heavier aircraft, and heavier aircraft means you need more lift force. You see that circular argument there? So in this case, to get the best possible aerodynamic performance, what's important is the ratio of these two forces, and you will see the importance of this more in our performance calculations. So in other words, if you increase the lift force by a factor of 2, it means nothing if the drag force is increased more. If the drag force is increased by a factor of 3, then your overall performance is worse. You need to make the ratio here, the lift to drag ratio, as high as possible. And again, intuitively you can see this, but you will see the importance of this in our performance calculations once we start studying them. So here in this paragraph I just explained what I just said earlier. So this wing is basically better, and that's because you have a smaller wingtip area. Okay, so now you may think, hopefully now you all understand the difference between 2-dimensional and 3-dimensional wing. Then you may question, why do we even care about 2-dimensional wing, since no aircraft can possibly have such a wing? So we will have to have a finite wingspan, and why do we even talk about 2-dimensional wing? The reason is the following. So I said in aerodynamic, the performance of a wing, the airfoil shape is important, and also the wing planform shape is important. And so when designing aircraft, you need to design these two things yourselves. If you are designing a new aircraft, you need to design the airfoil first, and then you need to design the planform area. But while you are designing the airfoil, you consider the airfoil performance only, independent of the performance related to the shape of the 3-dimensional wing. And when studying the airfoil performance, you automatically consider a 2-dimensional wing. So before designing the wing platform, you choose an airfoil, and while choosing an airfoil, you assume you have a 2-dimensional wing. Okay, after you choose the airfoil, you start worrying about the 3D wing shape. And while designing the airfoil, you need to consider airfoil data. Okay, so you need to choose an airfoil that gives you the performance that you need. And in doing so, you consider a 2-dimensional wing. And in practice, you can create data for 2-dimensional wing in a wind tunnel as follows. So this is a wind tunnel test section. So this rectangular box, the air is coming in this direction, and you have a certain cross-sectional area. Let's say you have 1 meter of width here. So if you place a wing section, and if you leave no space between the wing and the wall of the test section, your wing will effectively become a two-dimensional wing. Okay, so this is your test wing. Okay, so it has a rectangular planform, and the span, the wingspan of your test wing is equal to the separation between the walls of the test section. In this case, there will be no gap here, and practically this will be acting like a two-dimensional wing, because since there is no gap here, you cannot have these three-dimensional or these wingtip vortices created in a wind tunnel. So in this case, what you measure in the wind tunnel will give you the two-dimensional wing data. Okay, so you'll be effectively measuring the airfoil data only in a wind tunnel. And why do you need that? To be able to pick the airfoil for your wing. And after that, while designing wing planform area, then you need to consider the three-dimensional effect. Okay? So starting from next week, we will start arranging the wind tunnel tests. And in the wind tunnel test, you will be testing something like this. So you're going to put a wing section, a test wing in a wind tunnel, and it will be just like this here. It will be covering the entire width of the test section. So that means effectively you will be testing a two-dimensional wing. Okay? And if you want to measure three-dimensional data, then this is what you need to have. You need to have a model, and then you need to leave enough distance between the wingtip and the wind tunnel wall so that these vortices can be freely created. So if you want to create three-dimensional data in a wind tunnel, you need to use a much smaller test model as shown here. Okay, now let's take a look at how we can make the three-dimensional wing effects better, because they are clearly something that we don't want, because they decrease the performance. They cause the lift force to go down and drag force to increase. And if you compare these two wings here, the red distribution is the distribution of an ideal two-dimensional wing, where you have the same lift force everywhere. The blue one is the distribution of the actual wing. And these are the differences between them, right? So these are losses. These are the lift forces that you lose for having a three-dimensional wing. And as you see, compare the two, you can make these losses due to three-dimensional effects better by using a very high wingspan wing like this one here. So if you extend the wingspan as much as possible, then the area where you lose lift force will become smaller, as you see here, right? So if you compare the blue and red here, so I don't know, maybe here you're losing 20 or 30% of your lift force, whereas if you look at this case here, the area you lose is much smaller. So the losses here are less than 10%, right? So obviously it's better if you have a larger or longer wingspan. So here these are the top views. So this is a wing with a lower wingspan, and this has a higher wingspan. So to make these two comparable, you need to keep the wing surface area the same. Otherwise, you can't really compare them directly. So let's say if the total surface area of this wing and this wing are the same, then what is different between this wing and this wing is their aspect ratio, right? If you remember the definition of the aspect ratio, it is defined as b squared divided by the the wing surface area. So this is a low aspect ratio wing. This is a high aspect ratio wing because the wingspan is much larger. So the b number is larger for this wing. That makes this wing a high aspect ratio wing. Okay, so let me read this. If you compare the areas under the blue and red lift distributions, you will find out that for the red wing, for the wing on the left, you lose a bigger percentage of the 2D lift. So this is the same thing I said earlier. wingtip effects depend on how slender the wing planform is, which is measured by the aspect ratio. So obviously you can see that a high aspect ratio is good for smaller three-dimensional losses. And here you see an aircraft with a wing, with a very high aspect ratio wing. On powered aircraft, drag force is balanced by the thrust provided by the engines. However, gliders have no engines that can provide thrust force. Therefore, minimizing drag on gliders is crucial, and that's why they use very high aspect ratio wings. So this is the glider, and the glider is an aircraft with no engine. So this doesn't have a thrust force. So how they fly is they are towed to a certain altitude. So these are pulled by another aircraft or by some other mechanism with some cable. Like a kite, right? You take them up to a certain altitude and then you break the cable and then the glider can fly by itself without any thrust force. So in a glider, since you don't have a thrust force, having drag as low as possible is a very high priority. And if you consider this wing, for example, the lift force you lose and the drag force you get is much smaller compared to a low aspect ratio wing, right? So this is a very nice wing design in terms of 3D effects. So you may say, if a high aspect ratio is good, then why don't we make it as high as possible? Which is what we do, but for large aircraft, it's not practical to have such a high aspect ratio wing. So this is an airliner. So if you try to make the wing of this airliner a high aspect ratio wing similar to this one, then you'll have structural problems instead of the original wing here, which is shown here. You can make it better aerodynamically by increasing the wingspan as shown here, but as you see, it will lead to a very long and slender wing, and it will not be practical to have such a long wing, even though you know that this is going to be better aerodynamically. But to have such a thin and long wing strong enough, you need to make it heavy, and that brings a penalty, because additional weight is something you don't want. So you need to make the balance between structural preferences and aerodynamic preferences, and that's why the aircraft have wings of this shape, and they don't prefer wings with very high aspect ratios like the gliders. Mm-hmm.
How is the difference in terms of drag between low aspect ratio and high aspect ratio?
Well, I will come to that, but basically the high aspect ratio is better in terms of 3D effects. And 3D effects include a reduction in lift force and an increase in drag force. So it's bad for two reasons. And if you come back to this ratio here, you have a smaller lift force and an increased drag force. So that means this ratio becomes smaller due to two reasons. So the increase in lift, the decrease in lift and increase in drag, they both reduce the ratio. Okay, so in designing an aircraft, you need to find the balance for everything. I mean, if the only concern was aerodynamics, then you would probably choose a wing like this one here for your aircraft. But that's not your only concern. You need to worry about the structures as well. As I said, you can't make a very long wing such as this one strong enough. So you, considering the structural strength and the aerodynamic, to keep the balance between them, you need to make a compromise, and this is what they ended up with for this aircraft. Okay, Do you have any questions? Okay. So in our performance calculations, we need to put all this information into equations. Okay. So in this slide, you already see that aspect ratio is an important factor. So if you have a high aspect ratio, then you expect a better wing performance in terms of aerodynamics. And again, as I said, all this information needs to be put into equations so that we can use them in our calculations. So let's continue reading from here. High aspect ratio means that you have a wing that is closer to an ideal two-dimensional wing. In the limit, as aspect ratio goes to infinity, a three-dimensional wing approaches a two-dimensional wing. And as aspect ratio gets smaller, you get farther away from a two-dimensional wing. As you can see in this diagram here, the lift versus alpha plot at a given angle of attack for a low aspect ratio wing has a smaller lift coefficient than a high aspect ratio wing. Okay, so now let me just explain this plot a little bit. So there are three curves here, and the vertical axis shows the lift coefficient, and the horizontal axis is the angle of attack. So you'll be measuring something like this in your wind tunnel experiments. So you'll be making these plots similar to this one. So these three curves represent the effect of aspect ratio. So basically, if you start with a two-dimensional wing, which you can obtain in a wind tunnel as I explained earlier. So you make a wing, test wing that fills the entire test section, test area. So the data you collect for that will be a two-dimensional wing. So this is what you get, okay? And you use the same airfoil, but reduce, make it a three-dimensional wing. So instead of having a two-dimensional wing, you make it, so let me just remove these plots. So a three-dimensional wing, the data for this one is this curve here. You take that and make it a 3D wing, but with a high aspect ratio. It turns out that you get a data like this one here. So if you compare these two plots, you see that the lift coefficient is smaller for a given angle of attack. So for example, if you look at the data at 10 degrees, then the 42D wing, you have this much lift coefficient, whereas for the 3D wing, you have a smaller lift coefficient, which is reasonable, right? This is what we have been discussing so far. And if you make the aspect ratio even smaller, okay, so I'm talking about something like this. So this is a 3D wing with low aspect ratio. And that corresponds to this data. And this only shows the effect of the aspect ratio. And aspect ratio is just one parameter regarding the 3D effect. But there may be so I'm trying to decide whether I should continue with this subject or should I leave this until after the exam. So the next topic now is to quantify these differences. So if I give you two different wings, and while making performance calculations, you need to use certain parameters in equations that will reflect the differences between these wing designs. And at this point, probably it will be better if we leave this discussion until the next lecture. Okay. Okay, so apparently in the previous years I also talked about stall on this graph. So let me just do that here as well. So if you look at the data here, the original data, you see that your lift coefficient increases with the angle of attack, right? And then at some point it makes a peak and starts going down again. And the point where it reaches the maximum possible value is called the stall condition. Okay, so this is the highest lift value, lift coefficient value you can possibly get with this wing, and it is obtained at a certain angle of attack, and we call that the stall angle. And after that, if you increase the angle of attack any further, the lift coefficient starts going down. So this is the stall condition. And the drawing that I erased here was explaining that, so I can just draw that here again. So what happens there is you have an airfoil and you get a certain force, right? So you cause a deflection in the airflow, and this gives you the lift force. If you increase the angle of attack, then there will be a larger deflection in the airflow direction, right? So there will be more deflection, and that gives you more lift force. So you have a small lift here. So in this case you have a greater lift. But if you keep doing that, then what happens is, suppose that you bring it to a very large angle of attack. At some point the flow separates. Okay, that means the flow cannot follow the surface of the wing anymore, and what it does is it just detaches from the surface and it goes straight like that, leaving an empty area here, and this empty area is filled by some turbulent flow, and this is the reason for the stall. And when this happens, your lift force starts going down again, and this turbulence flow here causes the lift force to go down, and that's what happens when you reach this peak. So if you just look at this graph, you may feel like you get the same lift coefficients both here and here, right? So there are 2 points here, two angle values that give the same lift coefficient, this one and this one. But there's a difference actually between them, because this is before stall And for this, at this point, you will have a steady air lift force. But if you increase the angle of attack to here, even though on this graph it looks like you have the same lift coefficient, you will not have a steady force anymore. That's because of these vortices here, these turbulent airflow here. So let me make a new slide. Okay, so according to the CL alpha curve, both alpha 2 have the same so you get a steady lift force, whereas alpha 2 is after stall, so there's separated turbulent flow over the wing, which gives a fluctuating on average you get the same force but it will be a fluctuating force, and hence it will cause the aircraft to shake. So let me just draw this on a plot, on a time plot. So let me draw the situation for alpha 1. So you have a certain lift force. So this is supposed to be steady. This is for alpha 2. For alpha 2, okay? So on average, you get the same force, but the difference, there's a huge difference between them. So in this second case where the wing has stalled already, you have a wild turbulent flow over the wing, which causes the lift force to fluctuate very rapidly, and that will give you a rapidly changing or fluctuating lift force, and if an aircraft flying in that area will be experiencing wild shakings due to this changing force. Okay, so if an aircraft approaches the stall, the pilot can see that, feel that rather, due to the shaking of the wings. So once the pilot feels such shakings, then he should immediately feel that he's approaching the stall angle, and then try to correct for that as quickly as possible. Okay? All right. Okay, so hopefully now you understand why a three-dimensional wing is different than a two-dimensional wing, and how we can make it better. So hopefully these drawings convince you that you can make these losses smaller if you can keep the wingtip area as small as possible. And now the next thing we are going to do is we're going to put all this information into equations so that we can compare the performance of different wing types. So if you want to compare the performance of this aircraft with this wing to the aircraft with this wing shape, for example, then we're going to use these equations, and we will start talking about them starting from our next lecture. Okay? So let me stop here for today. Probably I will delay this until after the exam, so you will not be responsible for the 3D calculations in the exam, but after the exam we will start talking about them. Okay, so on Friday, please take a look at past midterm questions, and if you have any questions, come to class and we can discuss them in class, okay? And the exam will be at 10 a.m. in the morning on Saturday.